So this is lesson 8.4 of our calculus class. Unit 8 is called Differential Equations and Slope Fields. Lesson 4 is called Slope Fields. So we've talked about diffie-q. So now we're going to talk about what is a slope field and how do we read slope fields. All right, so if we're given a differential equation, it tells us the rate of change of an original function. However, if I take the antiderivative of a differential equation, the antiderivative is a set of functions, not just one particular function. So if we're given the differential equation of a function, we can't really graph the original function because it could be any number of functions within a set of antiderivative functions. And so what we can do is we can find what the slope would be at any given point on the graph. Because the theory is just about any point on the graph, since we have the set of antiderivative functions could be just about anywhere on the graph. So any point on the graph could be a point through which one of the antiderivative functions goes through, which is kind of confusing to think about. But what we can do if we just have the differential equation is we could find at any given point on the graph what would the slope of the tangent line look like at that point. And so to answer that question, we're going to sketch out on the graph what we call a slope field. And so the slope field at any given point, instead of putting a dot, we're going to draw a line that kind of represents what the slope would be of the antiderivative through that point. So for example, if the point 0, 0, so what would an antiderivative to this differential equation would go through the point 0, 0 at a slope that's pretty flat. And we get that if we take 0, 0 and we plug 0 in for x and 0 in for y in our differential equation, the answer is 0. So that means, again, whatever function or antiderivative function of dy dx, as it goes through 0, 0, it's going to go through at a flat slope. Similarly, the point 1, 0, whatever antiderivative function of our differential equation goes through the point 1, 0, is going to go through this point at a slope of 1/2. We get 1/2 by taking 1 for x and 0 for y and plugging it into our differential equation. And we can do that with a whole bunch of points. And if that makes sense, then you can see how tedious drawing a slope field or sketching a slope field by hand, how tedious that can become. So here's an example with just like nine points on the slope field. You could plug in any value for x, y, and so then any xy point with those xy values will give you a different slope, and we can sketch roughly what that slope would look like. The ultimate creation we've done with all those slopes sketched is called a slope field. So here's another example. If I have another differential equation, dy dx is x times y squared. I can pick any point for xy pairs, and I can plug those points into our differential equation, and I can obtain the slope of the antiderivative function at those particular points. And then I could sketch the slope field accordingly. Now if we flip that, you're given a slope field, and we have to ask, okay, which function, which differential equation goes with this slope field? Then we kind of have to come at this with a little more careful eye. We can pick out individual points on our slope field and see if they correspond with the differential equations. So for example, if I look at the slope field, I can see any point where x equals 0. In other words, any slope on the y-axis is going to be a horizontal line, which means any point where x equals 0, we're going to get a differential equation that equals 0, or the slope of a flat line, right? So I want to find, okay, when x equals 0, the dy dx is going to equal 0. And so that's going to be true for the first one, because if I put 0 in for x, we're going to get 0 squared. It's going to be 0 over something. That's going to be 0. It's going to be true for problem C, because if x is 0, 0 over anything is 0. It's going to be true for the differential equation D as well, because if x is 0, 0 times anything is also 0. But it's not going to be true for B. If x is 0 and x is in the bottom, we're going to be dividing by 0, and dividing by 0 is not equal to 0. It's undefined. So because of all these flat lines on the y-axis, I know that B cannot be the right answer. I also noticed there's no slope at the point 0, 3. So at 0, 3, there's just this open space, which means that um, the point 0, 3 on our differential equation would be undefined. So, all right, so which equation, if I plug in 0 for x and 3 for y, would we get an undefined equation? So that's here in green right here. We've already crossed off b, so we don't have to worry about that. If x is 0 and y is 3, we get 0 over 0, and that's undefined, so that would work. If we look at this one, x is 0 and y is 3, we get 0 times 0. And 0 times 0 is 0, but it's not undefined. So because of this hole right here, we can eliminate D as a potential option. So B is gone for our first reason, and D is gone for this new reason. So we're left with A and C. And you can really just pick any slope on this thing. I just happen to pick this one right here. This looks like the point 5, 5. So if you plug in 5 for x and 5 for y, we get a positive slope. It looks like it could be about 1 maybe, but it's definitely positive. If I plug in 5, 5 for a, we're going to get negative 5 squared over 5 minus 3. And so that, if we evaluate that, we find that's going to be, like it's really easy to see that's going to be a negative answer. But we know because of our slope field, the 0.55 is a positive slope. But if we plug in 5, 5 for this differential equation, we get a negative slope. So for that reason, we know that A cannot be the differential equation for this slope field, which leaves us with the answer of C. We can double check 5, 5 on C. If I plug in 5 for x, and if I plug in 5 for y, I get 5 over 5 minus 3 squared, or 5 over 2 squared, which is going to be a positive value. And so that is consistent with this point on our slope field. So since we eliminated A, B, and D, we know that C has to be the differential equation. And we could test any point on this thing and look at its slope. If we check, for example, 4, 3, we plug in 4 for x and 3 for y, we should get a positive number bigger than 1. If we plug in the point negative 3, 2, so x is negative 3 and y is 2, because of this slope right here, we know that the answer should be negative. We could test any point like that to see if this differential equation matches. All right, some takeaways. We can sketch slope fields, which are the go alongside a differential equation. The slope field represents the slope of the set of antiderivative functions to a differential equation at any given point on the graph. And hopefully now we understand how to read a slope field a little bit better.